Hello, one and all. This is Sarvesh, lecturer in Civil Engineering, Government Polytechnic, Station 1. And the course is Reinforced Concrete Structures. Today, I am going to discuss about the design of columns by limit statement. Right? After completion of this lecture, you are able to know what is meant by column and pedestal. What are the different types of columns and how to classify columns, and what is mean by effective length of the column, how it will affect on the strength of the column, and how to determine this effective length of the column, and what are the codal provisions related to the effective length of the column, right? And next, what are the different types of reinforcements are to be used in columns, right? So before going to today's topic, just recap what we were discussing last class. So till last class, we have discussed about the design of continuous beams. That is how to design a continuously reinforced rectangular beams as well as doubly reinforced rectangular beams. And we have seen the procedure for a design of continuous beams as per the method or coefficients proposed by IS 456-2000. And we have solved two or three solved problems for better understanding, right? And next, and we have seen the codal provisions while designing the continuous beam, right? Then we have discussed about the design of continuous slabs. That means how to design a continuous slab. What are the provisions proposed by IS 456. Then we have calculated the shear forces and bending moments as per the method proposed by IS 456-2000. That is based upon the coefficients which are given in IS 456-2000, 12 and 13, and based upon that we have calculated the shear forces and bending which are used to determine the reinforcement in a given section, right? Then we have checked for shear, and we have discussed the procedure how to check for shear in slabs as well as in shear design in rectangular. Then we have checked for stiffness, right? And we have checked for development length also. So these are the things we were discussed in last class, that is continuous beams and slabs. Now coming to the today's topic, that is column. Column is a vertical member which buckles and develops axial stresses. Sometimes it's a combination of axial stresses and bending stresses. See, just like a column, I hope we have already seen a lot of pictures in our previous lecture. It's column, a horizontal member. It is a part of a buildings, right? So as we discussed, different component parts of the building. That means if we start from bottom, first one is footings. Next, columns, plinth beam or basement, columns, beams, slabs, right? This is the construction process. First, we have to construct the foundation, right? Then columns, plinth beam, next beams and slabs. And loads transformation of a structure is from slab to beams, beams to columns, columns to footings to saw. So that is the construction, the load transformation process. And construction is footings, columns, beams and slabs, right? So it is a part of a structure and it is a vertical member which transfers the load, which takes the load from the beams and transfer to the footings, same, right? So generally the length of the member is quite higher as compared to its cross-sectional dimension, right? So that is why the column is a vertical structural member which carries compressive load and whose effective length is exceeds 3 times of its least lateral dimension, right? So it can be classified as the column. And again, if the effective length exceeds 3 times of its least lateral dimension, then we can call it as this column. That is the minimum dimension. That means if you see in a problem, it's plan, suppose this is your rectangular beam. So least lateral dimension is nothing but this is what is the least rectangle, right? So if it is exceeds, then we call it as a column. If it is less than 3 times the least lateral dimension, then it can be called it as pedestal. Pedestal is nothing but you can say it's a small column, right? It is also a vertical compression member whose effective length is less than 3 times the least lateral dimension, right? So generally pedestals, suppose if you see the cross section of a foundation, generally based upon my experience, see, so this is a cross section of a foundation of it. This suppose this is your footing, right? And suppose this is your column, for example. So generally, the pedestals are provided at this level, like this. So this is called as your pedestal, right? So generally, the length of effective length of the pedestal is less than the 3 times of the least lateral dimension, right? This is your column. This is your pedestal. So pedestal is provided to increase the strength of the column and thickness of the column, right? If the length is very high, the length of the column is very high. Therefore, you can provide a pedestal at the foundation, right? Now, coming to the classification. So, classic columns are classified based upon the 4 types. That is based on the shape of cross section and based upon the type of loading and based on the uh, type of loading, uh, based on the slenderness ratio, and based upon the pattern of lateral reinforcement, right? So what is mean by based upon the shape of the cross section? That means this is generally if you provide a square one, square shape, then you call it as a square column. If you are provided a rectangular one, for example, let us say this is a rectangular one. This is the length and this is width. Then we call it as a rectangular column. And next one is if you provide it as a circular one, then we can call it as a circular column. And if you provide, there is a composite column. That means composite means suppose you have a let us say it is a rectangular column, and if you provide some you can say some key section type, right? That means steel section, steel and concrete. Generally, this type of composite material columns are used where the industrial buildings, where the loads are very high, right? And at that cases, you can go for composite section, right? So these are the common type of cross sections which we are going to use in the field. So generally, we will go for rectangles. Most uh, uh, mostly we will prefer rectangles, and some cases you can go for square sections. And if there are any elevation purpose anything else, then go for circular one. And this is the used where you need to uh, carry the heavy loads like industrial buildings. So in that cases, you can go for composite section, right? And next one is type of loading. So based upon the type of loading, it has to be classified into two types. That means this is concentric loading and eccentric loading. Concentric loading means if the, let us say, axially loaded column. Suppose this is your column, right? If the load on a column is exactly coincides or it is passing through the centroid of the column, then we can call it as axially loaded column. That means there is no eccentricity, right? I think we have a clear picture. Yeah. So as I said, based upon the shape of the cross section, it has been classified into four types: square section, rectangular section, circular section, and composite section. And coming to the square section, so the side of a column is A, both sides, this one is A and this one is A. So therefore, area is equal to mark here, this is A square. And where L or H is the unsupported length of the column. So this is the length of the column, right? So this is called as ties, lateral ties. We'll discuss this one also. We will discuss longitudinal bar and lateral bar. So these are the main reinforcement, and this is called as the lateral. Right? Next is right. This is your square section of area B to B, right? And this is your circular section, a very important section. We will discuss. We will have a good discussion on circular column. Right? There are some specific codal provisions are there, and the area of the circular column is pi d square by 4, where d is the diameter. And coming to the, this is composite. See, so this is your rectangular, and in the middle you can provide the I section, and there are 4 main bars, right? Then you can pour the pump. This will carry a very heavy loads as compared to other sections. Next is, coming to the loading, axially loaded column, right? So axially loaded column and eccentrically loaded column. There are two types, right? Again, in axially loaded column, there are two types: column subjected to axial load and uniaxial bending, and column subjected to axial load and biaxial load. What is this? So if you see, this is the axially loaded column, right? Here, load acts through the axis of the column. That means, as I said, that the load uh, acts exactly at the centroid of the section. Suppose if this is your sorry, so say, see, this is the cross section, that is plan of a column. The load is exactly concentrated at the CG of the column or CG of the cross section. Suppose if it is a square, the load is exactly concentrated like this. So here is exactly acts at the axis along the centroidal axis of the column. Then we can call it as a axially loaded column. If you see the plans of different sections, whatever you are seeing, so that is for a square. And if you see in a plan, the load is acted exactly here, the center point. Here the load is act. Here also, suppose this is your center point, then right? So if the load is coincides with the centroid of the cross section along the longitudinal axis, then we can call it as this uh, axially loaded column. If it is not, then we can call it as eccentrically loaded column, right? In eccentrically loaded columns, again it is two types. That is biaxial or uniaxial. That is what we discussed. That is for eccentrically loaded column, there are two types: biaxial or uniaxial. What is meant by biaxial or uniaxial? We're going to discuss the eccentric. Eccentricity means if the load is acted away from the centroid of the centroidal axis of the column, right? Suppose if you see here, if you observe, this is your cross section plan of a column. So the centroid is here, but the point of action of load is like, right? That means it is away from the centroid axis, the centroid of the cross section of the column. So then we can call it as if eccentrically loaded column. Then what is the difference in structural point of view? How it differs? Because if it is an axially loaded column, then only compression will occur, right? Compression. But if the column is eccentrically loaded, there is a movement because you can design only related to the load acting on the member. Suppose if it is exactly at the centroidal axis, then you can design a column based upon the load directly, right? There is no extra loads. But if the load is acted at a distance of small e, let us say eccentricity, then due to this eccentricity, there is a bending moment developed about the centroid axis of the column or about the centroid of the column. Then you need to design a beam to resist the load which is acting on the member, plus that should be resisted by the movement also, because due to eccentricity the movement will develop about the centroidal axis, right? So that is why you, while designing you need to you need to remember these points. That means you need to decide whether it is a axially loaded column or eccentrically loaded column. And one more thing is, in eccentrically loaded column, there are two types. That is whether it is uniaxially loaded column or biaxial loaded. What is meant by uniaxial and biaxial? Uniaxial and biaxial means if the eccentricity is subjected to only about one axis. One axis means, suppose, so you have a column section, and let us say this is your cross section. Then if the load is acting somewhere else here, so suppose the load is acting here. Is it visible to you? I hope it's not. Let us see. So the load is acting here. That means it is, suppose this is your let's say this is your x-axis, this is your y-axis, for example, x-axis, and this is your y-axis, and the load is eccentric with respect to the y-axis, right, about this axis. So this eccentricity we call it as E of E, small e. So this is with respect to y-axis. Let us say I can call it as EY. So that means the load is eccentrically loaded with respect to y-axis. That means only one direction. That we call it as uniaxially loaded column. Uniaxial means the load eccentricity is only with respect to one axis, right? And if the load is in another case, let us say here right? And the load is acting at, let us say, at this point, for example, at this point. So this is your x-axis, this is your y-axis, right? So this is your eccentricity, E of, let us say, x with respect to x. So in these two cases, the eccentricity is uniaxial. That means the eccentricity with respect to one axis only, right? And this, due to this, there is a movement along y-axis, and due to this, the movement along x-axis. So due to here, it will rotate, right? And what is meant by biaxial? Biaxially loaded column means, let us say, suppose this is your column, and so if you see in a plan, this is your x-axis, this is your y-axis. Biaxial means the load is eccentrically loaded with respect to both the columns. That means somewhere else here, let us say, somewhere else the load is active, somewhere else here. Right? That means it is eccentrical with respect to, suppose, let us say, this is your E, that means this is x-axis, Ex, and with respect to this one also, this is Ey. Let us draw a bigger one for better understanding. So it's very important to understand whether it is a uniaxial or biaxially loaded column before going to design. So suppose this is your column and this is your x-axis, this is your y-axis, right? And the load is acting at somewhere else here. This is your P, let us say. So this distance called as P of x, and this distance we call it as P of, sorry, this is P of x, and this distance we can call it as P of y. So that means it is eccentrically loaded with respect to both the axes. Therefore, here you will get both the moments. That means moment with along the x-axis, bending moment along the y-axis. That is mx and my. So while designing, you need to take care about these bending moments also, right? If it is a uniaxially loaded column, right? So this is very important. And how to decide whether how to identify whether it is your column is eccentrically loaded column or axially loaded column. So load is acted through the point which is away from the axis in either direction, known as eccentricity, that is, we can represent it as in terms of small. So as per the codal provision, if we can allow a minimum eccentricity, that we call it as E minimum. So up to within the minimum, then we can, because see, in civil engineering, while constructing, it is very difficult to construct the exactly whatever we have drawn in software, because it is a practical, the designing software or designing the member is easy as compared, is different as compared to the execution. It is very difficult to construct exactly what we have designed in the system or we have drawn in the system, right? Because there are some other parameters that we need to consider while constructing. So that is why the code is also for constructing exactly axially loaded column. So it is given some some exemption. That means if E minimum is within the permissible limit, then we can design as a axially loaded column. If the E minimum is greater than the whatever the eccentricity which is developed within the member is greater than the minimum eccentricity which is provided in IS 2000, then we should design that column as a eccentrically loaded column. So that should be calculated by E minimum should be greater than or equal to L by 500 plus D by 30, where L is and subjected to a minimum of 20 mm. That means, as per the codal provision, if the eccentricity is within the minimum or 20 mm, we can design that column as a axially loaded column. If it is exceeded, then we can design as a eccentrically loaded column, right? So here L is the unsupported length of the column. We will discuss what is the unsupported length of the column. D is the lateral dimension on the direction under consideration, right? And this is important. E minimum should be less than or equal to 0.05, where D is the lateral dimension. Generally, we can consider as lateral dimension, right? And E should be less than or equal to 0.05 D, right? I think this we have discussed it, and E should be greater than E minimum or 0.05 D. Then we can design that column as a eccentrically loaded column. Otherwise, we can design as a axially loaded column, right? Next is classification based on slenderness ratio, right? So what is meant by slenderness ratio? So far, the slenderness ratio is nothing but it is the ratio of effective length of the column to the least lateral dimension, right? So effective length of the column to the least lateral dimension. What is meant by effective length? Effective length, okay. Effective length we have to calculate as per the coded provision by least lateral dimension. That means if you see in the plan, so which one? This is a dimension, lateral dimension. This is, let us say, width and breadth. So whichever is this, that should be considered as least lateral dimension. And based upon the L effective by the ratio or the slenderness ratio, the columns are classified into two types, that is long column and short column. Why we need to classify whether it is long column or short column? Because the performance of the member for long column and short column is different. Because when you apply the load, it's just like if you take a small rod or whatever it is, you just suppose if you have a small stick, you can take as a stick, a small very thin stick, and you can put your hands here and here and just press it. Then what will happen? It will try to bend like, right? Whatever the shape, it will try to bend like, right? Similarly, you just take a small stick, very small stick. In that, you can take very small stick and you can put your both hands between the hands and press it. Then what will happen? The performance difference, right? In long column, it will bend like this, but in short column, it cannot bend it. Just compress it, right? So that is the difference. The short columns failure due to crushing. If you apply more load, then it will crush it. Just like if you take a small piece of right, any soil wound and you can just press it, and what will happen? It will crush, right? So the failure pattern will change based upon the type of the column, right? If it is a long column, the long column will fail to buckle. This is called as buckling, right? So the long column fails due to buckling and short column fails due to crushing. So that is why before design you need to know what is the type of the column based on the slenderness ratio, whether it is a long column or short column, right? So this is also very important parameter you need to remember while designing the column. Next is coming to the slenderness ratio. Then right, if the slenderness ratio is less than 12, that means that L effective by least lateral dimension is less than 12, then we can call it as short column. That means lambda is equal to L effective by D, or LEX by D is less than or equal to 12, then we can classify uh, the column as short column. That means it will fail due to crush. And if the slenderness ratio is greater than the 12, that means lambda is greater than 12, then we can classify as long column. That means it will fail due to buckling, because the strength of the column is depends upon the type of the column, whether it is long or short, because it is depends upon the lambda, right? So that is what is given. You see, the short columns are failed, essentially failed by compression. That is nothing but crushing, right? And the long columns fail by buckling. Just have shown figure na buckling. So the long column will fail due to buckling. Now coming to the fourth one, that is the pattern of lateral reinforcement. Because based upon the placement of the reinforcement, the columns has been classified into two types. That is, sorry, one is column with lateral ties, and one other one is column with helical ties or reinforcement. This is exclusively for circular column. What is meant by lateral ties? Because it's own introduction, so that is why I'm not going to very deep. So just would like to give a glance on what is meant by lateral ties. So you just recall what just recall in beams. In beams, we have provided the shear reinforcement, right? Just so this is a beam, let us say, whether it is a single reinforcement or double reinforcement, whatever it is. So what we have done is, this is the longitudinal bars. Then we have given, so these are called as what is this? These are the shear reinforcement. Because in beams we have designed the shear reinforcement also, that we can call it as uh, stirrups, right? So same ring, whatever we are designing, same ring we will use in columns, but the name we can change it as lateral ties. So suppose if this is your column, right? So if you see in this cross section, so the reinforcement is provided same as our beams. So this is your reinforcement provision, and around this reinforcement you need to provide one which that we call it as, in columns we can call it as lateral ties, right? But the performance is different. The purpose of providing lateral ties and stirrups is different for beams and columns, right? So here the lateral ties is this one. So if you provide a just ring, that means then we can call it as lateral ties, right? Whether it is circular column or rectangular column, whatever it is, if it is a circular column, uh, you have to provide it like this. And this is your main ring or longitudinal bar. This is called as your lateral ties, right? These two are the lateral ties. So then we can call it as the column with lateral ties. Then what is mean by longitudinal? Sorry, what is another type? that is helical tie. This is a special type of reinforcement which is provided in circular columns only, right? We cannot provide in rectangle square columns. We can provide only in circular columns. What is meant by helical reinforcement is, so if you have a column and you have a longitudinal reinforcement, right, and you have a lateral ties, right, for circular columns, which is as usual. In addition to the lateral ties, there is another reinforcement bar which is provided periphery of the reinforcement. That means this would like to say, and it will provided like this. So this is called as this helical reinforcement. So the purpose of providing helical reinforcement is to increase the load carrying capacity of the member, and it will increase the stiffness of the member. It's just like if you take a rod, there is a rod, and you just tie a what we call it. You can tie a thread or any wire like just like round. So for example, you take just simply see you just round it, right? If this is your column, then you can round it like this, right? So that is called as helical reinforcement. The purpose is it will increase the load carrying capacity of the column and increase the stiffness of the member, right? So just see the diagram. So this is your uh, longitudinal bars. This is your lateral. This is longitudinal bars. See here, this is longitudinal bars, and these are the lateral ties, right? So longitudinal bars is main bars, which we take with our compression bars, are tied with the lateral ties. So lateral reinforcement, or we can call it as transverse reinforcement in columns, right? So see, these are called as lateral ties, which ties with the compression bars, right? So the distance between these two, we call it as pitch. The distance between the center to center distance between the two lateral ties, we call it as pitch, right? And next is helical reinforcement. Just now, as I told just now, here the transverse reinforcement is in the form of helix or spiral, or we can call it as a spiral reinforcement also. So these are the main bar. So this is the actual diagram. You can provide like it can be extended up to the top. So if you see the plan, yes, I would like to draw a plan. So if this is your column, right, and having a, how can I say that? So having a, so we can have, I will try to show. So these are the, let us say, bars, and which can be provided. So sometimes we can provide in circular columns, we can provide helical reinforcement with lateral ties, or without without lateral ties with helical reinforcement. Here you can see there is no lateral ties, right? Only helical. So if you see similar to the, so this is your uh, the helical reinforcement without lateral ties. Or if you take another column and you just do the reinforcement, and you have a lateral tiles, and above that one you have to provide the helical reinforcement, right? So this is the helical reinforcement, and this is your lateral tile. This is combination of helical reinforcement and lateral tile. This is only the helical reinforcement, right? So this is the transverse reinforcement is in the form of helix or spiral, right? So you can if you provide, then the strength of the column is increased, right? So this is how you can do it, right?